For the type of reactor used in the process, which is steam reforming process and water gas shift process, the type of reactor used are packed bed reactor. The usage of packed bed reactor is suitable for gas-solid reaction and use primarily heterogeneous phase reactions with catalysts. The advantages are high conversion per unit mass of catalyst, low operating cost, and continuous operation. For the type of catalyst used for steam reforming reactor, we use nickel oxide, and for water gas shift reaction, we use iron oxide doped with chromium oxide. For the description on how the reactor separator system works, it is a cylindrical shell with a thickness that permits reactant to flow via continuous into extreme. It has a cooling jacket that employed to remove heat from the reactor. It saves costs on catalyst purchases while producing more desired product, and the conversion of product per unit mass of catalyst is high. SMR produces hydrogen, carbon dioxide, and a little amount of carbon dioxide, while from the water gas shift reaction, carbon monoxide and steam reacted to produce carbon dioxide and additional hydrogen. By using PBR, which allows for constant mass flow rate of reactants within the reactor, it lessens the chance of formation of undesired products since it can be formed right after the desired products are formed.
Next is the sizing of the reactor. Since both of the reactions take place in two different reactors, the volume of the reactors were calculated separately. Now let's see how we calculated the volume of packed bed reactor for SMR reaction. Assume that the SMR reaction operated at 900 degrees Celsius and 30 atm with a conversion of 98%. In calculating the reactor volume, the 5-step methods can be applied. The first step is to generate mole balance. For PBR, by assuming that there is no accumulation, the mole balance equation can be further simplified in terms of weight of catalyst. Next, the second one is rate law equation. By referring to references, the rate law for SMR reaction can be calculated as follows. The third step is regarding the stoichiometry of the reaction. It has been given that the production of hydrogen gas is 30,000 tonnes per year. By assuming that the molar ratio of methane and water is 1:3, a stoichiometric table can be developed, and from the table, we can obtain initial and outlet flow rate, outlet concentration, and outlet composition of the component. This schematic diagram includes both inlet and outlet total flow rate and both inlet and outlet composition of the components. After that, we can combine all of the steps above to calculate the weight of catalyst. The weight of nickel oxide catalyst for SMR reaction obtained is 17.3 kg. The catalyst has a volume of approximately 2.6 mm3. To calculate the volume of the PBR, the equation of gas hourly space velocity can be used, in which for SMR reaction, the space velocity is 11,600 per hour, as suggested by reference. The volume of PBR obtained is 0.639 m3. Hence, the proposed design is feasible, as the volume occupied by the catalyst is much lesser than the volume of reactor. For WGS reaction, similarly, 5 steps method can be used. Assume that WGS reaction operated at 400 degrees Celsius and 10 atm with conversion of 98%. By taking the outlet flow of SMR as the inlet flow of WGS reaction, the calculations of the 5 steps method are as follows. The weight of iron oxide catalyst for WGS reaction obtained is 189.143 kg, in which it occupies 0.036 m3 of volume. Meanwhile, the volume of PBR obtained is 1.568 m3. Thus, it can be concluded that for both reactors, the proposed design are feasible as the volume occupied by the catalyst is much lesser than the volume of reactor. In maximizing the selectivity and yield of hydrogen gas and minimizing the side reaction, strategies can be made based on Le Chatelier's principle, where changing the conditions such as pressure, temperature, or concentration of products or reactants, the position of the equilibrium shifts in the opposite direction to counteract the change. Therefore, for SMR reaction, the operating temperature can be increased as it is an endothermic reaction. the operating pressure can be reduced and the concentration of CH4 can be increased. By doing so, the equilibrium will be shifted to the right side and it will favor the forward reaction to occur. Consequently, more hydrogen will be produced. Meanwhile, as WGS is an exothermic reaction, the operating temperature can be lowered so that the equilibrium will be shifted to the right side. Moreover, for both reactions, removing the hydrogen produced as soon as it was formed will also shift the equilibrium to the right side. Hence, higher yield of hydrogen can be achieved.
Assalamualaikum warahmatullahi wabarakatuh. I'm Ahmad Hanif bin Hanafi. I'm going to explain on the process modeling and simulation subject. The process flow diagram of this process will be shown as here. Some of the assumptions were made for this process. For the first one is the natural gas feed into the stream is purely methane, which is sulfur free. The second one is the water feed is sufficient for the process, so there is no water treatment will be added in the simulation. The third one is the reactant is in a plug flow. The fourth one is the gas, all of the gas behaves as an ideal gas, no heat loss by radiation to the surroundings. The packed bed for both SMR and WGS unit will be simulated as PFR, which is plug flow reactor, and last but not least, the mixture in the reactor is perfectly mixed. The assumptions for the material streams and its properties is shown as the slide here. Next is the assumptions for the unit operation, which is heater and SMR unit with its properties, and then for the assumption for unit operation cooler and WGS properties as shown in the slide here. Deviation error is performed by comparing the manual calculation from Reaction Engineering 1 subject with the calculated value obtained from the symmetry simulation software. First, we are going to compare the conversion value from both manual calculation and the value obtained from the simulation by using this conversion value formula here. For the SMR unit, the conversion value assumed on the Reaction Engineering 1 subject is 0.98, and the conversion value calculated based on symmetry simulation software is 0.99. And then, for the WGS unit, the conversion value assumed from the Reaction Engineering 1 subject is 0.98 as well, and the conversion value calculated based on symmetry simulation software is 0.98. Next, we are going to compare on the reactor volume based on the manual calculation and the simulation calculation. From this table here, both of the reactor volume for the SMR and WGS shows a 0% error, which indicates that this simulation and the manual calculation is tallied to each other, and same goes to the conversion value for both SMR and WGS, which shows an approximately the same value for the conversion value. Next, for the sensitivity analysis, these are the list for the independent and dependent variables. For the effect of WGS feed stream pressure on the mole fraction of hydrogen at WGS outlet, the graph will be shown as here. When the WGS feed stream pressure increase, the mole fraction of hydrogen at WGS outlet will increase as well. Based on the Dalton's law, the partial pressure is directly proportional to the molar fraction and the total pressure. So here, when the partial pressure of the carbon monoxide produced from the SMR unit increase, the pressure or the total pressure of WGS feed stream will increase as well. This will increase in the mole fraction of the carbon monoxide, which yields in a higher conversion of hydrogen in WGS. So the mole fraction of hydrogen in WGS outlet will increase. Next, for the effect of WGS feed stream temperature on the mole fraction of hydrogen at WGS outlet stream, the graph will be shown as here. When the WGS feed stream temperature increase, the mole fraction of hydrogen at WGS outlet decrease. Since the water gas shift reaction or WGS is both reversible and moderately exothermic, the reaction requires a low temperature in order to advocate the forward reaction. So here we can relate it based on the equilibrium constant formula and the Dalton's law. So here is the derivation of the formula. According to Lickitelius' principle, when the temperature increases, the equilibrium will shift in such way in order to decrease the temperature. So, as a result, the equilibrium will be shifted to the left, causing the yield of both carbon dioxide and hydrogen to be decreased. So, it will lower the equilibrium constant. So, when the equilibrium constant decreases, the mole fraction of carbon monoxide and hydrogen will decrease as well. Thus, hydrogen production at the outlet stream of WGS will decrease. For the effect of mole fraction of inlet methane on the mole fraction of carbon monoxide at SMR outlet stream and the mole fraction of hydrogen at WGS outlet stream, the graph will be shown as here. When the mole fraction of inlet methane increase, so the mole fraction of both carbon monoxide and hydrogen at the SMR and WGS outlet will increase as well. This is because when the mole fraction of inlet methane increase, the methane to steam ratio will increase. Thus, more methane will be in contact with the steam. So, when methane will be more contact with the steam, there will be an increasing in the effective corrosion between the methane and the steam. So, the rate of reaction will increase. When the rate of reaction increased, the production of both carbon monoxide and hydrogen will increase as well. So that's why the mole fraction of both carbon monoxide and hydrogen at SMR and WGS outlet increase. Therefore, for the effect of molar flow rate of inlet methane on the mole fraction of carbon monoxide at SMR outlet and mole fraction of hydrogen at WGS outlet, the graph will be shown as here. When the molar flow rate of inlet methane increase, the mole fraction of carbon monoxide at SMR outlet and the mole fraction of hydrogen at WGS outlet will increase as well. This is because when the molar flow rate of the reactant increase, the molar flow rate of product will increase as well, based on the law of conservation. Therefore, when the molar flow rate of methane increase, the mole fraction of both product, which is the carbon monoxide and hydrogen at the SMR outlet and the WGS outlet, will increase as well.
For separation process part, it's going to be explained by Eunice and me, Victor. The properties of outlet water gas stream taken from simulation is shown as below, which is going to enter the dry unit. The process flow diagram for absorption process is generated by doing the mass balance for each component.
The pressure swing absorption unit has been selected to extract the hydrogen gas. Some assumptions have been made such as obey ideal gas law, no radial variation in temperature, concentration and pressure, bed and absorbent particle have uniform porosity. The isotope selected is the Langmuir isotope as it provides a perfect fit for experimental data of carbon dioxide gas absorption with the assumption of absorption energy on the absorbent surface is uniform and remain unchanged. The general equation of the Langmuir isotope is as shown as in the slide. Apart from that, activated carbon with pellet size of 3 mn have been selected as the absorbent as it is commercial and low-cost absorbent that exhibit higher carbon dioxide gas absorption capacity. Besides, it is widely used to capture carbon dioxide gas due to each large surface area per unit volume. The submicroscopic probe provides more external surface area too. The summary of the design of absorption column and the absorbent have been shown in this table.
I plotted the breakthrough curve of CO2 absorption by activated carbon at 35 degrees by referring an online article. The TB, TT, and TD was plotted out. The assumptions for our calculation is also listed as below. First, TU and TT was obtained from the graph. The mass of CO2 absorbed is then calculated by using the molar mass of CO2, which is 44 kg per mole. The saturation capacity is then calculated by dividing the mass of adsorbed solute by the mass of an absorbent. We then calculate the volume of activated carbon occupied to find the total bed length by using the area of 1 meter cube and the density of activated carbon assumed to be 1.97 gram per cm cube. The diameter and mass transfer zone and used bed length is also calculated. Lastly, followed by the calculations of unused bed length, which is 2.538 meter. To validate the purity of H2 produced, the flow rate of H2 at outlet stream is divided by the total flow rate at outlet stream. At last, we get 99.92%, which achieved the question requirement.
The first strategy to achieve 99.9% purity of hydrogen gas production is by recovering hydrogen trapped in absorbent after absorbent reaches its limit absorption capacity. First, hydrogen is repressurized and purged into another absorbers. The bed is partly regenerated. The absorbed impurities are rejected into the PSA of gas. The absorbent is then purged with high purity hydrogen. Then the absorbent is repressurized with hydrogen before ready to the next absorption step. The next strategy will be shorten the absorption time as shown in the graph attached. When the time increases, the absorbent bed will be partially saturated as part of the carbon dioxide gas trapped will escape and mix together with the hydrogen gas, giving rise to a drop in hydrogen gas purity. Therefore, increasing in absorption time has an adverse effect on the hydrogen gas purity but benefit the hydrogen gas recovery. The desorption process is important to remove the absorbed pollutant in order to recover the original absorption capacity of the absorbent and allow the reuse of absorbent instead of replacing it, and the desorbing agent used in this case is the supercritical carbon dioxide. In the regeneration process, activated carbon is dried and heated up until it volatilizes 75 to 90% of the adsorbed material. Steam is then injected to the activated carbon and is ready to be reused.